So this problem right here, we have a container with a fluid inside, right? And so this container will be spinning with an angular velocity omega, and as it spins, it will create this concave shape. And we're supposed to find the maximum velocity at which this container can spin, or angular velocity at which this container can spin, in order for the fluid not to spill out. So we need to find maximum angular velocity at which the fluid can stay in the container. So the original height of the container, or the height of the container in general, is h, big H I should say. The original depth of fluid is d, but as this container spins, it will create this concave shape, and this area right here will have a depth of little d, or a height of little d, and this whole area right here, as this fluid is spinning, it actually distributes throughout this concave shape. So we'll be focusing on this area right here, right? And so from this point here, that entire area gets volume of pi r squared d that will be distributed throughout the concave shape. So we'll focus on this specific part right here. So let's find the volume of this area right here. And so let's draw a little diagram. So we are traveling from the center of this container to the outskirts of it. And so this will be 0 for the center to the outer part of the container, which is just r. I should probably write that here too. And so that can be our start for our integral. It's going to go from 0 to r, right? So what are we measuring? Well, as we're going and changing and measuring at different values of r, we are actually measuring dr. And so think of it as like we're pushing against that water to that outer part of the container. And so we're actually measuring two values of dr in order to find the surface area, we should say, of this little measurement we're taking. And as we're taking different measurements of dr, we are getting different surface areas. And so the surface area would be 2 pi r times this by h, right? And we are taking it at different values of dr. So we can actually plug that into the integral. And h in this case we found in a scenario from class, h would be equal to omega squared over 2g times this by r squared. And so we can plug that into the equation. 2 pi r, plug in h, omega squared r squared over 2g dr. And then from here, make sure it's still recording, cancel out the 2's, and then we can pull out our constants. So our constants in this case would be pi, and we are assuming that the velocity stays constant, so omega squared can go out, and gravity obviously doesn't change. So bounds stay the same, multiply the r's together, and you get r cubed, dr still stays in there. We can then integrate. By doing that, we will get 1 over 4 times this by r to the 4th power same bounds. And there we get the final expression, pi omega squared times this by big R to the 4th power times this by 4g. And again, this is the volume of this area that is being distributed throughout this concave shape. Pi big R squared times this by, I keep forgetting, D, sorry, it's been a long day. And so we want to find the height of this little area. And so by doing some simple rearranging, we can find that height. So those pi's will cancel out. This will cancel out. This will reduce to 2. So with this, little d will be equal to omega squared big R squared over 4g. This will be the height of this area, right? And so, again, I want to re-emphasize big H. We don't want the fluid to go over this container that has a height of big H, right? And so, in the scenario when the container is spinning, we'll have new parametrics to measure, right? That being the height of the actual concave itself. We'll call that little h. And the space in between the bottom of the concave to the bottom of the container, that will be d minus little d. And so we set that equal to big H. So big D minus little d plus little h will equal h, right? So let me just create more space here. All right. So big D minus little d. We found little d to be omega squared R squared over 4g. And then plus h, little h. H we found over here. H is omega squared R squared over 2g. I actually did make a mistake a while ago. This is supposed to be just big R, not little r. And then all of this is equal to big H. So we need to find the angular velocity. So what we do here, we subtract d from both sides. We get h minus d on that side. Then we combine these two values together. So we multiply this by 2 over 2 to make common denominators. And on the bottom you get 4g. And then we can add these two values together. This will be this entire value times 2, but then since we're subtracting it by this value, we'll just get omega squared R squared over 4g. That'll be our left side of the equation. And so we need to isolate omega. And so, rearranging, multiply both sides by 4g, you get h minus d times this by 4g, divide this, both sides, by r squared, and when you square root, you get the final expression, which will represent the maximum velocity at which the container can spin so that no fluid spills over.